Welcome to How to Treat Concrete Floors, sponsored by Rust-Oleum. As we delve into the intricacies of concrete treatment, we'll explore the latest techniques and products that are shaping the future of our industry. Whether you're a seasoned professional or new to the field, today's session is designed to enhance your knowledge and skills. So let's embark on this educational journey together and discover the best practices for treating concrete floors to ensure durability, aesthetics, and long-term performance. Thank you for joining us. Hello, I'm Jay Allred. With over 40 years' experience in the coatings industry, I've had the privilege of witnessing and contributing to its evolution. I hold several industry certifications, including the AMP Senior Coatings Inspector credential. My career has been shaped by incredible mentors who've instilled in me the importance of knowledge, technical responsibility, and the value of sharing what I've learned. Currently, I serve as an architect and engineering business specialist at Rust-Oleum, where I share my insights on industry trends and developments to our clients. Concrete floors require protection. Choosing the right concrete floor coating system is essential to meeting performance requirements of commercial, industrial, and residential environments. This course discusses the assessment and repair of a concrete floor and specifies how to select a high-performance coating system based on conditions and requirements of a construction project. Topics covered in today's presentation include common problems with concrete, moisture in concrete, why is concrete coated, applicable standards, types of high-performance coating systems, selecting a high-performance coating system, and applications for high-performance coatings. Credit for this course is 1 AIA HSW CE hour. At the end of this program, participants will be able to discuss problems associated with concrete construction and describe how they impact a concrete floor's appearance and performance. Evaluate how to control and possibly conquer the biggest problem that concrete has as a surfacing material. Recognize the differences between the technologies of a variety of high-performance coating systems for concrete floors and discuss their potential uses, and identify the design criteria needed to properly specify a high-performance coating system for a concrete floor based on the needs of the application. Concrete floors are an important element of the construction market. These floor applications include residential flooring, garage floors, interior floors, sidewalks, and patios, commercial flooring, retail markets, hospitals, restaurants, and kennels, and industrial flooring, manufacturing plants, breweries, and mechanical rooms. The total concrete market, both in flat work and vertical applications, is dramatically increasing again with more steady growth. The demand for concrete floor coatings is primarily led by the growth in the construction industry and increasing awareness about floor coatings. Growth in construction activities pertaining to commercial and residential sectors is expected to drive the demand for concrete floor coatings. This course explores concrete floors, including different coating technologies, how to specify the correct coating, and basic problems that always occur with concrete surfaces. Concrete is primarily made up of three elements: water, aggregate, and Portland cement. The ratios of these elements must be properly proportioned in order for the concrete to reach its maximum durability and hardness. The chemical process in which concrete hardens is called hydration. Hydration is the chemical process in which concrete cures. The following is a general guideline for the curing process. Initial set is when primary crystallization occurs. The concrete can still be displaced with a sharp tool. Green state is when the bulk of hydration and evaporation of the water of convenience occurs. More importantly, it is during this period that the internal stress is created due to shrinkage. Contraction joints must be cut within this period. Initial cure is the period when the concrete reaches its rated strength. Fundamental cure is when the concrete reaches the majority of its compressive strength. Portland cement forms a water-impervious paste about 6 months under normal conditions. In the presence of moisture, concrete will continue to hydrate for as long as 90 years, reaching a compressive strength of over 9,000 psi. If any of the concrete elements are modified during the mix-in or hydration process, the concrete could possibly fail prematurely or experience problems. There are many factors that influence the durability of concrete. A few of those factors include the composition of concrete and exposure to physical and chemical conditions. Both of these factors will affect the concrete's durability and service life. In general, concrete is designed to resist most natural and man-made environmental and physical conditions. However, all concrete will experience some deterioration over time and should be properly coated to maximize its service life. Three of the most common types of concrete deterioration in commercial, residential, and industrial environments are scaling, spalling, and cracking. Concrete can be compared to a sponge, since like a sponge, a concrete slab can absorb moisture. When the moisture that a concrete slab absorbs comes into contact with the embedded reinforcing steel rebar, the conditions necessary to establish a corrosion cell are created. This typically leads to the formation of rust on the steel rebar. As the embedded steel corrodes, it expands and generates sufficient tensile pressure to rupture the surface of the concrete. This type of surface delamination is also known as spalling. Since the main cause of spalling is moisture, the application of a protective coating will help prevent the premature failure of the slab. Spalling is similar to scaling, except the expansion occurs from deeper within the concrete, causing the surface to disintegrate into larger fragments. Common causes of rebar corrosion are due to carbonation, intense heat that causes water vapor to expand violently, improperly constructed joints, and crack deterioration. If spalling exists, it must be addressed before a coating is applied. Many companies offer fast-setting repair products. Scaling is local flaking or peeling of a finished surface of hardened concrete as a result of exposure to cycles of freezing and thawing. When the hydraulic pressure of the expanding ice exceeds the tensile strength of the concrete, scales of mortar detach from the surface, exposing aggregate. Generally, it starts as localized small patches which later merge and extend to expose large areas. The term dusting is used to describe the presence of a powdery material on the surface of a hardened concrete slab. Dusting may occur when a weak layer of cement paste, latents, is left on the surface of the slab due to overworking the concrete during the pour. This weak layer of concrete paste can dust under traffic, causing a loose powder to form on the surface of the slab. The dusting shown in this photo is an extreme case, most likely caused by a deterioration of the latents formed from overworking the concrete during the construction phase. The most effective treatment for this slab is to remove the thin, weak latents layer and then apply a coating for future protection. The surface discoloration of concrete can be caused by many factors. Remember, concrete is like a sponge, so any foreign liquid or material that comes into contact with the surface has potential to stain it. Discoloration due to oil and grease stains is very common. When the concrete slab is left unprotected with the absence of a sealer, the concrete slab lacks the ability to resist the stain. The discoloration of concrete shown in this photo is most likely caused from an automobile dripping fluids onto the stamped concrete slab. The most effective treatment for this floor is to remove the oil residue with a steam or topical treatment, and then to apply a sealer to prevent any future potential stains from soaking into the slab. Efflorescence describes a crystalline deposit on the surface of the concrete that appears after water-containing water-soluble salt deposits migrate through the slab and evaporate. After evaporation occurs, the salt deposits are left on the surface of the slab, giving it a whitish appearance. The migration of water through a concrete slab is normally caused by the absence or failure of a moisture vapor barrier in the slab floor design. This photo of efflorescence shows the salt deposits on the surface of a concrete slab. Efflorescence is a bond breaker for coatings and will need to be removed before applying any coating. The proper way to remove efflorescence is with a stiff broom and/or high-pressure washing. Crazing is characterized by a fine network of random cracks on the surface of a concrete slab. Crazing is caused by carbonation, a naturally occurring process that occurs when the Portland cement paste in concrete is exposed to the carbon dioxide in the atmosphere. Carbonation creates a weak latence on the surface of the slab and can promote crazing. Carbonation can also be caused by shrinkage of the surface layer, inadequate curing, or an excess concentration of cement paste and fines with an overly wet concrete mixture. In this close-up photo of crazing, the cracks formed in the weak layer of cement paste can easily be seen. The fix is to remove the top, thin layer of the slab with a grinder and apply a coating. Alkali silica reaction, commonly known as concrete cancer, is a harmful swelling reaction that occurs over time in concrete between the highly alkaline cement paste and the reactive amorphous silica found in many common aggregates, given sufficient moisture. This deleterious chemical reaction causes the expansion of the altered aggregate by a formation of a soluble and viscous gel of sodium silicate. This hygroscopic gel swells and increases in volume when absorbing water. It exerts an expansive pressure inside the silicous aggregate, causing spalling and loss of strength of the concrete, finally leading to its failure. The key to slowing down ASR is to choke off the moisture source. Breathable coatings can also help to mitigate further damage. Pozzolans are silicate-based materials that react with or consume the calcium hydroxide generated by hydrating cement to form additional cementitious materials. Most concrete slabs will crack over time. To help control cracking, construction or control joints are typically placed in the concrete surface at predetermined locations. However, cracks can occur in unexpected areas of a slab due to poor design or poor grade compaction. There are several types of cracking, from cracks that occur on the top layer of the slab to cracks that reach grade level. All cracks in concrete are a concern, as cracking can lead to further deterioration of the concrete surface and the possible total failure of the concrete slab. Cracks in concrete are caused by many factors, including ground settlement, poor preparation of the soil, and an improper mixing of the concrete. The root cause of the crack must be determined and corrected before the application of any coating. In addition, it is necessary to determine whether a crack is static or dynamic. Static cracks usually affect only the surface of the concrete and can be repaired easily, but dynamic cracks can be serious, may run through the depth of the slab, and could represent a structural problem. A dynamic crack, if not repaired, will eventually reappear through a surface coating. There are many sources of moisture in concrete, both internal and external. External sources may include rainwater intrusion, humidity in the air, groundwater, spills, plumbing leaks, or poor drainage. The internal source of moisture in concrete is the mixing of water, the water of hydration and the water of convenience from the original concrete mix. The water of hydration is the amount of water needed to complete the chemical reaction between the water and the cement to make concrete form a hard surface. The water to cement ratio is the ratio of the weight of water to the weight of the cement that will affect the drying time of concrete. At 0.5 water to cement ratio, concrete will take 1 month for each inch of concrete thickness to dry. Since the industry agrees that a 28-day cure time is acceptable, it's easy to see how moisture could still be trapped in the slab and why moisture testing is so important. The water of convenience is the quantity of additional water that is mixed into the concrete to make it more workable, fluid enough to pour and finish. Typically, water can be chemically bound to cement with approximately 25 pounds of water to every 100 pounds of cement. The amount of water that must be added to physically bind all of the ingredients in concrete and provide workability can be an additional 25 to 40 pounds. The extra water can affect the performance of the concrete and how long a slab takes to cure. Moisture vapor transmission is another internal source of moisture in concrete. Excess water in the concrete rises as water vapor to the surface of the slab. Once a slab is covered, vapor can collect and condensate under the covering, causing blistering, peeling, and flooring failure. Moisture can move up through the slab, both on and below grade. The rate of MVT is determined by both humidity and temperature. In general, moisture moves from a high temperature to a low temperature and high humidity to low humidity. Moisture can rise upward through a concrete slab by capillary action. Moisture rises through the concrete's capillaries, or hydrostatic pressure. The slab acts like a sponge and draws water upward from all damp areas below, including the surrounding soil. ASTM F1869, standard test method for measuring moisture vapor emission rate of a concrete subfloor using anhydrous calcium chloride, is a commonly used test in the United States for measuring the moisture content at the surface of a concrete slab. It is a simple test that, when performed properly, will yield a pounds of moisture vapor transmission per 1,000 square feet value. Most floor coatings have an acceptable value of 3 pounds per 1,000 feet. Although this is an acceptable test, the results are based on a snapshot in time and may give false positives. So flooring failures due to excess moisture in concrete could still take place when the environmental and ambient conditions within a building or concrete slab change. The slab must be open and absorptive prior to performing the test. 3 tests must be completed within the first 1,000 feet, and 1 within each additional 1,000 feet. Testing requires 72 hours to complete and must maintain occupied temperature and humidity conditions during the test. Most flooring manufacturers require a maximum of 3 pounds per 1,000 feet. ASTM F2170, standard test method for determining relative humidity in concrete floor slabs using in situ probes, also known as the in situ probe test or RH test, measures the amount of moisture in a concrete slab by placing sensors or probes in the slab itself. This method of testing is less sensitive to short-term fluctuations of ambient and environmental conditions, provides a quantitative result, and is widely accepted in the industry as being a reliable, accurate test for providing overall slab moisture levels. Typical industry requirements are 75% or less relative humidity. 3 tests must be completed within the first 1,000 feet and 1 within each additional 1,000 feet. Holes must be drilled to 40% of the slab thickness and vacuumed before the probe is inserted into the hole. The probe must be left in the hole for 72 hours prior to recording the results. Most flooring manufacturers require less than 75% relative humidity. So why do we coat concrete? Concrete coatings can offer protection, waterproofing, ease of cleaning, dust control, decoration, slip resistance, and safety. Vapor barrier coatings reduce moisture vapor emissions from a concrete slab to an acceptable level so a coating system can be applied. For example, a vapor barrier coating can be designed to reduce moisture vapor emission levels up to 28 pounds per 1,000 square feet and reduce them to 3 pounds per 1,000 square feet. Most vapor barrier coatings are specially formulated high build epoxies and are one-coat application. To note, vapor barrier coating manufacturers may require moisture vapor emission testing of the concrete slab prior to the application of a coating. The pictures here show a before and after. In order for concrete to reach the maximum life cycle, the concrete must be protected from both environmental issues and intended concrete usage. Concrete needs to be protected from several types of elements. These include moisture penetration from rain and snow, chemicals from spills, and abrasion and wear from foot and vehicle traffic. By applying coatings to concrete, the life cycle of the concrete can be extended because the coating acts as a wear or sacrificial layer, protecting the concrete from stains, abrasion, and moisture intrusion. Coving can be invaluable in protecting walls from serious damage. By facilitating proper washdown and cleaning of equipment and the space itself, floor coving supports overall food safety and consumer health. Concrete, because of its porous nature, is very susceptible to staining. Concrete coatings seal and protect a concrete surface and help to keep a concrete floor looking clean and stain-free. The sealed surface is easy to clean with a broom or mop. Coating systems give concrete a durable layer of protection against heavy traffic, abrasion, chemicals, and moisture exposure. Decorative concrete coatings can offer protection and add a unique finish or aesthetic to any interior or exterior concrete. Concrete can be decorative and functional at the same time. Slippery surfaces can be problematic, from floors and steps to surfaces exposed to water or those with grease and other contaminants sitting on them. The fear of dangerous, slick concrete surfaces on retail and commercial properties can be eliminated with a slip-resistant coating. A slip-resistant coating is designed to create a non-skid surface while providing protection and durability against daily wear and tear. It gives a floor texture and hides imperfections, stains, and discolorations. Textured coatings can meet the Americans with Disabilities Act requirements for non-slip coatings and can be applied with a brush, roller, or sprayer. Consult individual coating manufacturers for details about products that meet ADA requirements for non-slip coatings. Concrete floor coatings can create safer working environments by providing slip resistance, offering antimicrobial functions, and increasing light levels. In this warehouse, The light gray floor reflects light from the open doors and the overhead lighting and bounces it back into the interior space, providing workers with better lighting over their work area. The first step in these operations is extremely critical. The best materials correctly mixed and applied are doomed to fail unless the concrete substrate is properly prepared. At a minimum, the concrete substrate must be prepared in compliance with minimum standards for the system to be placed per ACI, ASTM, ICRI, PCSI, and AMP standards. Deleterious surface contaminants and deteriorated concrete must be removed, repaired if necessary, and the surface roughened and cleaned. There are many different techniques, methods, and types of equipment which can be used to effectively prepare concrete. Shot blasters, water blasters, scarifiers, grinders, and acid etching are some of the commonly used equipment and testing techniques for surface preparation. Using the correct standards for any coating system being specified is of great importance. This SSPC/NACE standard details the requirements for surface preparation of concrete by mechanical and chemical methods before the application of bonded, protective coatings or lining systems. The standard details specific methods of surface preparation as well as the amount of surface cleanliness and profile achievable by each method. The specifier is responsible for choosing the appropriate class of surface preparation from Table 1 for the intended protective coating and intended surface conditions, and these should be agreed upon by all parties involved, the owner, specifier, manufacturer, and contractor. The requirements of this standard are applicable to all types of cementitious surfaces, including, but not limited to, cast-in-place concrete floors and walls, precast slabs, masonry walls, shotcrete surfaces, and cementitious grouts, overlayments, and underlayments. SSPC highly recommends that individuals involved in the coatings and surfacing industry obtain ICRI Guideline Number 310.2 guide for selecting and specifying concrete surface preparation for sealers, coatings, and polymer overlays, text and physical profile samples. The most common guidance for the required profile for each coating thickness is also found in the standard, which assigns a concrete surface profile number based on the coating to be applied. The document further defines profile with physical replica specimens prepared with different surface preparation techniques. The higher the CSP number, the more aggressive the profile. Concrete substrate profiles, at a minimum, must comply with ICRI Guideline Number 310.2. However, SSPC does not recommend detergent scrubbing or low-pressure water cleaning or acid etching as a standalone method of surface preparation. These processes can only be used in conjunction with others. So what exactly are the ICRI Technical Guideline comparators? ICRI Technical Guideline Number 310.2 provides 9 distinct profile configurations that may be produced by one or more surface preparation methods. As a set, these profiles replicate degrees of roughness considered suitable for applying one or more of the sealer, coating, or polymer overlay systems up to a thickness of 1/4 inch. Each profile carries a CSP number ranging from a baseline CSP1 through a CSP9. To test for pH at the surface of a concrete slab, use wide-range pH paper, its associated pH chart, and distilled or deionized water. Place several drops of water on a clean surface of concrete, forming a puddle approximately 1 inch in diameter. Allow the puddle to set for 60 seconds, then dip the pH paper into the water. Remove immediately and compare to chart determining pH reading. Other pH testing methods, such as pH pencils or pH meters, or both, are available and may be used to measure pH. Bare concrete should be tested for pH and have a level between 7 and 11 before coating. The direct tensile strength of the concrete substrate should be determined prior to placement of coatings and surfacing materials. When the test is performed on the surface of a concrete repair or an overlay material, it determines the bond strength to the substrate or the tensile strength of either the overlay or substrate, whichever is weaker. The test specimen is created by drilling a shallow core into and perpendicular to the surface of the substrate, leaving the intact core attached to the concrete. A steel disc should be bonded to the top surface of the test specimen. Next, a tensile load is applied to the steel disc until a rupture occurs. Film thickness gauges, mechanical and digital. The main function of a coating is to provide corrosion protection by adhesion to the substrate. It is critical that the applied thickness be sufficient to ensure corrosion protection as well as proper adhesion. Film thickness is measured to ensure its compliance with manufacturer's TDS, project specifications, and various standards. Traditionally, a destructive test method was used to determine paint thickness on masonry substrates, such as concrete. Coatings used on concrete range from hard to soft, smooth to textured, and cover a wide thickness range. The surface of concrete can be quite rough, which can create significant variations in thickness measurements. A wet film thickness gauge is a tool that is designed to measure a liquid coating's thickness in the easiest and fastest manner. It measures the thickness immediately after the coating has been applied on a material. A non-destructive test method eliminates the need to repair the paint and coating system after inspection, saving time for both the inspector and the contractor. Over time, an exposure to the elements exterior concrete can develop cracks due to temperature changes, ground movement, improperly placed joints, and excessive loads. Once a crack develops, it is important to seal the crack from water to prevent further deterioration. What's best for filling cracks in concrete? Wide cracks in concrete are best patched and sealed with a concrete patching compound. Smaller cracks, less than 1/4 of an inch wide, can be repaired with a concrete caulk or liquid filler. Patching compounds typically are mixed with water and applied with a trowel. For larger cracks, a crack bridging membrane can be used. Crack bridging membranes are flexible epoxy membranes that are designed to provide protection to the upper layers when the concrete and other materials move and shift. They can also be used in conjunction with a fabric to help bridge the crack. A construction joint is a type of joint that is used when a new section of concrete is poured adjacent to another concrete section that is already set. The purpose of a construction joint is to allow for some horizontal movement while being rigid against the rotational and vertical movement. An expansion joint is an assembly designed to hold parts together while safely absorbing temperature-induced expansion and contraction of building materials and vibration, or to allow movement due to ground settlement or seismic activity. Contraction control joints are placed in concrete slabs to control random cracking. A fresh concrete mixture is a fluid plastic mass that can be molded into virtually any shape. But as the material hardens, there is a reduction in volume or shrinkage. An isolation joint is a separation between adjacent sections of a concrete structure to allow relative movement in 3 directions and through which all of the bonded reinforcement is interrupted. Expansion joints should always be sealed and filled with a flexible joint sealer over backing rod and filler, never epoxied or coated over. Other joints can be treated as you would with crack repair. Always refer to your specified product TDS. Here is a pictorial overview of many of the steps involved in the installation of a floor coating. Each of these steps should be taken into consideration when creating or reviewing a specification for a floor coating. From surface preparation to the mixing of the product to the proper application techniques, each element is an important step in the installation process. Always refer to product TDS. Flooring selection considerations. First, determine the project objectives. Define with the owner and other interested parties what success means on this project. Mock-ups can help all parties decide what can be done and can serve as a test bed for different techniques, materials, and cost versus performance results. What are the site conditions? What types of surface preparation methods must be used to prepare the concrete substrate for the application of the coating? Preparation of the concrete substrate to meet the specification requirements by both the coating manufacturer and the specification itself can be the costliest phase of a coating project. A manufacturer's surface preparation steps and guidelines may be written into a specification, or they can be found in a product's technical data sheet. Most coating manufacturers require testing for moisture in the concrete slab prior to the application of a coating. If the test results exceed a coating manufacturer's recommended tolerances, a barrier coat will need to be applied. What are the floor's performance requirements? High traffic applications usually require a coating system with more layers than one specified for low traffic application. Increased costs in materials and labor may be incurred. What is the installation schedule or return to service time? What level of abrasion and chemical resistance is required? What level of slip resistance is required? Will the floor be exposed to sunlight throughout the day? Is the floor a decorative element of the space? What colors, blends, or stains are desired? Are any functional markings like arrows or lines or logos required? What are the expected maintenance practices of the projected life expectancy for the floor? And what are the owner's overall expectations? It is also important to consider functionality versus aesthetics. Every flooring project is different, and sometimes both cannot be achieved. Aesthetics, the final appearance of the surface, is more important than many people perceive it to be. How an owner thought the floor was going to look versus the final appearance is sometimes widely divergent. Today, the same performance characteristics can be attained with a variety of decorative appearances and surface textures. Installation parameters. In many cases, a flooring project has a very tight installation schedule. This limits many systems in how long it takes to install a given material. In occupied areas, the odor of some solvent-based systems or the inherent odor of the material itself will limit its use. Temperature of the surface at the time of installation is critical in selecting a material. Some systems, such as epoxies, are very temperature sensitive and can vary widely in cure time at lower temperatures. Life expectancy. Owners want a flooring system that will last forever and will be guaranteed. In actuality, a given system will require maintenance periodically. Maintenance procedures must be clearly outlined and understood for a realistic life expectancy. Economics. Economy is the top requirement. At times, low-cost systems will prevail at the expense of more durable systems. Generally, when other parameters are exhausted, you get what you pay for. Another generally accepted maxim is that the thicker the applied system, the better performance. Sustainability. Responsible product innovation has led to the development of new technologies that minimize environmental impact. This section of the course provides an overview of features and benefits of the various types of high-performance coating systems designed to treat, protect, and enhance concrete surfaces. Epoxy, polyurethane, polyaspartic, polyurea, urethane concrete, and stain and polishing. Epoxy coatings. Epoxy coatings are the most common type of floor coating, and their ease of application makes them contractor-friendly. Epoxy coatings have several benefits. They are durable and adhere well to a variety of substrates, including quarry tile, plywood floors, and concrete. Epoxies are used for interior applications only and will eventually break down when exposed to ultraviolet light. This must be considered when specifying an epoxy coating in an environment where the floor may be subject to long-term exposure to sunlight from windows and doors. Epoxy coatings are self-leveling with no lap lines and can give a concrete floor a glass-smooth finish. With most epoxies being 100% solids, epoxies can be used for applications where product odor is a concern, like healthcare facilities. Slower drying times can be cost prohibitive. Floors that require multiple coat systems could take days before being returned to service. On the left, there is an epoxy flake system with colored flakes sandwiched between epoxy within the floor for decoration. This creates a slightly rough surface to prevent slips and falls. The middle photo is a metallic epoxy. This is a special multi-layered epoxy floor coating system that incorporates the use of metallic additive mixed into a clear epoxy coating to create exotic effects. To the right is a heavy-duty 100% solids Novolac epoxy. These coatings stand up to the harshest chemicals in extreme industrial environments. The highest level of protection against the most corrosive industrial chemicals, even 98% sulfuric acid. Polyurethane sealers provide an abrasion and chemical-resistant surface to a decorative concrete or resinous flooring system. They are available in matte, satin, and gloss finishes. Polyurethanes are very versatile products. They can be used as solid and clear top coats over epoxies, provide UV resistance, and aesthetically enhance coating systems. They can be water-based or solvent-borne. Polymer systems. When specifying a floor coating, the intended use and return to service time is important. Polymer systems, especially polyaspartic, a blend of polyurethane and polyurea coatings, have benefits that exceed epoxy coatings in return to service times. Many polyaspartics can dry in as little as 12 hours, but their installation costs can be as much as double that of an epoxy. Polyaspartic coatings offer several benefits such as UV stability, resistance to abrasion and impact, and resistance to harsh chemicals including salt, motor oil, gasoline, MEK, and acetone. In some applications, polyaspartics are applied over epoxies to increase the chemical resistance of the epoxy. Polyaspartic coatings can be applied in a wide range of temperatures, from -20 to 130 degrees Fahrenheit, and will not melt when exposed to high heat up to 350 degrees Fahrenheit. They are also flexible and allow for natural concrete movement without cracking or peeling, making them an ideal system for either indoor or outdoor applications. On the left, this fire station required a floor that could hold up to constant abuse from heavy fire trucks and equipment. A polyaspartic coating enabled the station to return to service quickly. Here in the middle, a clear polyaspartic coating over bare concrete. And this photo on the right shows a clear polyaspartic coating as a top coat. Polyurea. A chemist would define polyurea as a type of elastomer derived from the product of reacting an isocyanate component with a synthetic resin blend component. The isocyanate can be aromatic or aliphatic in nature. The result is a rubber or soft plastic compound that may be used in many of the same ways as older protective coating technologies. Polyurea is extremely durable, 20 times more than epoxy. Polyurea is also 98% more flexible than epoxy because polyurea is an elastomer. It can be applied by spray or roller at temperatures between -20 to 100 degrees Fahrenheit and in high humidity. As a fast dry coating, it can be top coated in 2 to 4 hours, and it provides excellent adhesion to concrete, fiberglass, wood, epoxy, urethanes, and polyurethanes. Polyurea. For floors, this coating technology can be used in a wide variety of applications. Not to be confused with truck bed liner polyurea. This coating technology provides reliable performance in all aspects of the floor coating industry, including industrial and chemical manufacturing plants, primary and secondary containment, retail environments, residential and heavy commercial buildings, protective coatings for metal and wood, as well as thin film clear coats over a large list of substrates. Polyurethane concrete. Polyurethane concrete systems are used for heavy industrial and commercial use applications. These types of floor coatings are applied in thicknesses up to 3/8 of an inch and can be twice as strong as concrete. Polyurethane concrete is much harder than concrete, with a pound-force per square inch strength reaching 7,500 psi or more. Polyurethane concrete systems can withstand the thermal shock inflicted by a range of weather conditions and the force of hot or cold high-pressure washing. They are well suited for wet areas where worker safety is a priority, or for heavy industrial applications where the long-term durability of the concrete floor is a concern. Common applications include production areas, manufacturing plants, loading docks, pharmaceutical plants, chemical processing plants, food processing areas, commercial kitchens, and bottling areas. Stain systems are a great alternative to solid color coatings. Stains offer a unique look and vivid colors that cannot be achieved with any other types of coatings. When paired with a urethane top coat sealer, they create a coating system that is very tough and resistant to most chemicals and levels of traffic. A single component, solvent-based stain system typically cures to a high gloss and is solvent resistant, equivalent to a 2-part urethane system. Stain systems offer rapid return to service times. They are UV stable and extremely durable. Solvent-based stained concrete floors can resemble expensive, highly polished floors, but they can be created at a more economical price point. Due to the clear top coat, stain coating systems also resist staining, a problem with many types of polished floors. One thing to keep in mind when choosing a stain system, as the one on the right, is to understand how important mock-ups can be. In most decorative systems, it is difficult to duplicate what was approved versus what goes down on the project. Communication as to variables and acceptance of those variables is paramount. Polishing concrete is very similar to sanding wood. Machines equipped with diamond segmented abrasives, akin to sandpaper, are used to grind down concrete surfaces to the desired degree of shine and smoothness. As when sanding wood, you gradually progress from coarser grit to finer grit. In this case, grit is the particle size of the diamond. The result is a glossy, mirror-like finish. Sodium and lithium-based products are formulated to extend the longevity of the concrete flooring while enhancing its appearance, durability, and ease of cleaning. These products deliver easy application, quick return to surface, and transform new and existing concrete with increased hardness, improved stain resistance, and long-term abrasion resistance. Sodium versus lithium densifiers. The sodium-based silicates give a slower action, and the lithium densifier has a faster reaction with the concrete. Both densifiers achieve the same effect, but sodium is best for porous concrete, and lithium works better for dense concrete. Common applications for high-performance coatings. As you can see here, high-performance coatings can be used in a wide variety of areas. Commercial facilities. As mentioned, a concrete coating installed on the floor in a commercial application must be able to withstand the daily operations of the facility. These activities may include chemical cleaning and hot pressure washing, used to ensure a bacteria-free, clean environment and heavy foot and mechanical traffic. On the left is an example of urethane concrete floor coating. Floors in food and beverage applications must remain clean and sanitary at all times, be able to resist microbial growth, and remain durable to withstand repeated exposure to potentially corrosive cleaners. In addition, they should have non-slip properties for added worker safety. Here is an example of a urethane concrete floor coating in a food service environment. Industrial plants. Manufacturing and industrial applications demand a floor coating product that can stand up to rigorous environments and tolerate the wear and tear of everyday traffic. The floors must protect worker safety with a slip-resistant finish and be chemical resistant. Floor coatings in industrial plants are often used to define aisleways, workspaces, and traffic flow to enhance safety while brightening up the interior and highlighting a facility for customer visits. Facilities for animals. Animal holding hospitals, veterinarian clinics, and dog kennels require floors with coatings that can withstand the wear and tear of a variety of animal traffic and a facility's stringent cleaning methods. The floor coating product must also be in low volatile organic compounds and low odor, and its application cannot leave any harmful solvents within the cured coating film. Retail environments. Concrete floors in retail environments such as this automotive shop require protection from high traffic and exposure to automotive fluids and other chemicals. In the middle is an example of 100% solids epoxy coating with a full chip broadcast. It welcomes customers into this commercial retail building. Some retail environments can pose unique challenges for a concrete coating. If the proper coating system is not specified, the expected life of the coating and the floor can be reduced significantly. To protect the concrete floor from the caustic nature of swimming pool chemicals in this pool supply store, a polyaspartic top coat was applied, as you can see in the photo on the right. Residential concrete floors. Concrete floors in residential applications are increasing in popularity as homeowners look for alternatives to traditional tile and carpet floor coverings. Garage floors are one of the few open areas visible to neighbors. A high-performance coating on a garage floor can enhance a home's curb appeal while providing long-lasting protection to the concrete surface. Here's an example of a water-based, low VOC and low odor epoxy with a sparse chip broadcast. As we conclude, you should now be able to discuss common problems associated with concrete construction and describe how they impact a concrete floor's appearance and performance. Evaluate how to control and possibly conquer the biggest problem that concrete has as a surfacing material. Recognize the differences between the technologies of a variety of high-performance coating systems for concrete floors, and discuss their potential uses, and identify the design criteria needed to properly specify a high-performance coating system for a concrete floor based on the needs of the application. If you have any questions, a list of resources is available upon request. Thank you for your time. This concludes the American Institute of Architects Continuing Education Systems course.